Good afternoon, everyone. I hope that your week is going great so far. Also hope that everybody's still doing good. We're looking here at the final lesson in this modified course. It's called the binomial theorem. This lesson is important for those of you going on to take Math 31 next year. There are a few of you that are currently in grade 11. And this lesson is also important for those of you in calculus right now because you're going to run into the binomial theorem in post-secondary math. Now, normally I would do the binomial theorem over 2 days, but I've whittled it down to what's essential. There is an actual formula that you can apply to what we're going to learn today, but I'm not going to teach you the formula. This lesson is on page 41 of your lesson handout. We're going to start off by looking briefly at something which is called Pascal's triangle. Pascal's triangle is an array or a pattern of numbers that has many, many applications in mathematics. The first 5 rows of Pascal's triangle are given here for you. So row 1 has 1 entry, row 2 has 2 entries, row 3 has 3, row 4 has 4, row 5 has 5. So there are the same number of entries or items in the row as the row number. Every row starts and ends with the number 1. There are some other patterns you can see. You can see one of the diagonals is 1, 2, 3, 4, and it would continue to be 5, 6, 7, 8, etc. Some of the other diagonals would be a little more complicated to explain. But the first question that we have to do as a warm-up is to complete the next 4 rows of Pascal's triangle and explain how each entry in Pascal's triangle is arrived at. So I would ask you sincerely here to approach this as a puzzle, to pause the video at this point in time and ask yourself if you can figure out what numbers to put in the next row. Hopefully what you discovered is that in order to find an entry in a row below, you add together the 2 entries that are adjacent to that entry you're trying to figure out. So this next entry is a 2 because 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 2 is 3, 1 plus 3 is 4, 6 is what you get when you add 3 and 3. Once you've seen that that is the pattern, it's fairly easy to figure out what the missing entries are. This would be 1. 1 plus 4 gives you 5. 4 plus 6 gives you 10. 6 plus 4 gives you 10. 4 plus 1 is 5. And then it ends in a 1. So all of these are going to begin and end with 1. The grid that I've provided here in this handout and the grid that I have on the screen is just there to keep us kind of organized. 1 plus 5 is 6, 5 plus 10 is 15, 10 and 10 is 20, 15, 6, 6 and 1 is 7, 6 and 15 is 21, 15 and 20 is 35, another 35, another 21, another 7. You'll notice, of course, that the entries in any individual row form a symmetrical sequence of numbers. For example, in the 5th row, it's 1, 4, 6, 4, 1. It reads the same forward as it does backward. The final row would be 1. 1 and 7 is 8. 7 and 21 is 28. 21 and 35 gives 56. 35 and 35 is 70, another 56, and then another 28, and another 8, and then finally the 1. And it's hard to believe that this puzzle, this pattern of numbers, has any significant meaning in mathematics. What we're going to learn about it today is only one significant application of this array of numbers. There are many others. Let's take a look at question 2. Question 2 gives you some information, and the first information is that if you were to take x plus y and raise it to the 0, anything raised to the 0 is 1. All right. If we were to take x plus y as a binomial and raise it to the 1, we get x plus y. And I'm choosing to write x plus y as 1x plus 1y. If I take x plus y and raise it to the 2, what that means is I have to multiply x plus y by x plus y, which means I'm going to FOIL out x plus y times x plus y and get x squared plus xy plus xy plus y squared. And when I simplify that, I get 1x squared plus 2xy plus 1y squared. If I wanted to know what x plus y cubed is, what I would have to do, and I'm not going to do it, but I want to explain to you where it comes from, what I would have to do is take x plus y squared, which we've already figured out as this, and multiply it by another x plus y. This would give us x plus y quantity cubed. And if you did that, what you would get is 1x cubed plus 3x squared y plus 3xy squared plus y cubed. And I want you to notice that the coefficients that we get in all of these binomial expansions form all of the numbers that we see in Pascal's triangle. I just noticed that I didn't put a 1 over here. Let me put a 1 in there. Not that it really matters. I know that you were aware there's a 1, but I'm going to put it in anyway. So the first row of Pascal's triangle gives you the coefficients of the expansion of the binomial x plus y to the 0. The second row gives you the coefficients of the expansion of the binomial x plus y to the 1. The third row is for the expansion of x plus y to the 2. So that's a little bit sneaky, that the row number is not matching the exponent on the binomial. Let me drive that point home. This is row 4, this is row 3, this is row 2, this is row 1. But when you take a look at the exponent on the binomial, in row 1 it's an exponent of 0, in row 2 it's an exponent of 1, in row 3 the exponent is 2. So the exponent on the binomial is 1 less than the row number that predicts the coefficients of the expansion. So now we're asked to predict, based on that, what the expansion of x plus y to the 4 would be, and then expand it to verify our answer. We're not going to expand it algebraically. We're going to go to the internet to find out what it's equal to. Okay, so we're just continuing the pattern. If I extend this now and look at row 5, that would be representative of x plus y raised to the 4, and we could certainly write out the coefficients by extending Pascal's triangle. So it starts with a 1 and ends with a 1. The 4 is found by adding these two numbers. The 6 is found by adding these two numbers. This 4 is found by adding these two, and then it ends with a 1. Now what we're going to do is take a closer look at the variables and the exponents. I'm going to pick on row 4 to illustrate this, but you'll pick up on this idea fairly easily. In row 4, the exponent on the binomial is a 3, and x in the first term is raised to a 3, and then x is raised to the 2, and then x is raised to the 1, and then the last term has x raised to the 0, because there are no x's. On the other hand, when you look at the exponents on y, the exponent on y in the first term is 0, then the exponent on y is a 1, then it's y to the 2, then it's y to the 3. So as the exponent on x starts at the maximum number it could possibly be and decreases by 1 each term, the exponent on y starts at being nothing and increases by 1 each time. So the first term of this would contain x to the 4, y to the 0. The second term would contain 1 less x and 1 more y. The third term would contain even 1 less x and even 1 more y. The next term would contain 1 less x and 1 more y. And the final term would contain 1 less x and 1 more y. And if you've done your job right, a number of things are true of each term. When you add the exponents together in each term, you will get the exponent on the binomial. The exponent on this binomial is a 4, and when I add 4 and 0, I get 4. When I add 3 and 1, I get 4. When I add 2 and 2, I get 4. 3 and 1 is 4. 4 and 0 is 4. That's going to be important for later. So the coefficients are the numbers in Pascal's triangle. The exponent on x starts off as being the exponent on the binomial, and it drops by 1 each term. The exponent on y starts off being 0, and it goes up by 1 each term. So what we ended up getting for our answer was 1x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the 4. And if I were to look up what x plus y to the 4 is, I can go to a website called Wolfram Alpha. I've already bookmarked this. I can type in x plus y raised to the 4. I can scroll down until it expands it out. There's a lot of other things too, but there is the expanded form. I'll kind of put it near the center of the screen so you can focus on it. X to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4. It works, and it's not a fluke. This continues to work beyond the 5th row. So when expanding x plus y to the n, there's always going to be, by the way, I didn't mention this, n plus 1 terms. When we look at the expansion of all of these binomials, when the exponent on the binomial, which we're going to call n, by the way, from now on, when it's 0, there is 1 term in the expansion. When it's 1, there are 2 terms in the expansion. When it's 2, there are 3 terms in the expansion. So that's an important idea behind the binomial expansion. There will always be 1 more term than the exponent on the binomial that you're expanding. The coefficients of the terms are the numbers from the n plus 1th row of Pascal's triangle. What does that mean? It means if you're expanding x plus y to the 5, you're going to look at the 6th row. If you're expanding x plus y to the 8, you're going to look at the 9th row. The first term will always have x to the n, where n is the exponent on the binomial expansion, and y will be raised to the 0, and each successive term has an increase in the exponent on y and a decrease in the exponent on x until you reach the last term, which will be x to the 0, y to the n. All right, example 1, expand x plus y to the 5. Well, we're going to have to look at the 6th row of Pascal's triangle. There's a downside to this method that I'm teaching you right now, and we'll find an easier method a little bit later in this lesson. The downside is that you have to know the 5th row to find the 6th row in Pascal's triangle. And if you don't know the 5th row, then you have to find the 4th row. And this goes back to the beginning, and you almost have to build it each time. Now, I happen to remember that the 5th row was 1, 4, 6, 4, 1, but let's build it. It's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. There's that 5th row. So the 6th row will be 1, 5, 10, 10, 5, 1. This is the 6th row. So what are the terms of this binomial expansion going to be? It will be 1 x to the 5 plus 5 x to the 4 y to the 1 plus 10 x cubed y squared plus 10 x squared y cubed plus 5 x to the 1 y to the 4 plus 1 y to the 5. So I want to go through what just went on in my head as I was writing that down. The first thing is these numbers, 1, 5, 10, 5, 1, are the coefficients of all of the terms. You'll notice, by the way, that there are 6 terms because the exponent was 5. The second thing I want you to notice is that when we look at the exponent on x, the first term had a degree of 5 for x, then 4, then 3, then 2, then 1. And then the last term, I didn't write it, but I could have written x to the 0. When you look at the exponents on y, I didn't write y to the 0 in the first term, but I could have written y to the 0. Then it's y to the 1, then it's y to the 2, then it's y to the 3, then it's y to the 4, and then it's y to the 5. That's a pretty powerful tool you have in your mathematical arsenal right now, because prior to today, if I said expand out x plus y to the 5, that would be a mathematical nightmare. You have to take x plus y times x plus y and FOIL it out. Then you have to multiply that trinomial you get by x plus y, which in and of itself is going to be quite the feat. And then you have to take that new one and multiply by x plus y again, and then multiply by x plus y one more time. If you understand what's going on here, getting the answer is very, very quick. All right, let's take a look at 3r minus 2t raised to the 6th. So I've upped the game here a little bit. It's not just x and y, it's something else. And I want to point out to you, everybody, that what we are doing here is always comparing things to x plus y to the n. And that means in question B, my x is really 3r, and my y is really negative 2t. My n, by the way, is 6. So if n equals 6, that means we are dealing with the 7th row. Well, I don't really feel like building Pascal's triangle again. If we look at the previous question, the 6th row was 1, 5, 10, 10, 5, 1. So if the 6th row was 1, 5, 10, 10, 5, 1, the 7th row, which is what we need, is 1, 6, 15, 20, 15, 6, 1. These are the numbers that I'm going to have as the coefficients on my expansion of the binomial. 1, 6, 15, 20, 15, 6, 1. I'm going to need a little bit of room here because I have more terms, and it's also not just x and y. So I'm going to have 1, and then I will have x, which is actually 3r raised to the 6. My next term will start with a 6, and it will have 3r raised to 1 less, which is 5. Notice that I'm putting that 3r in brackets. It's not just the r that's going to be raised to the 5, it will also be the 3. I also need to now multiply by 2t raised to the 1. Plus, my next term starts with a 15. Then I have my x, which is really 3r, raised to 1 less than the previous term, which would take it to a 4. And then I have my y, which is negative 2t, raised to 1 more than the previous term, which is a 2. Then my next term starts off with the number 20. And my x, which is 3r, continues to decline in value. So my x in the first term is a 6, then a 5, then a 4, now it's a 3. My y started off with 0, then 1, then 2. Now my y is a 3 as well. Plus, I have more to go. I now have 15, and then my 3r. Last time it was a 3, now it's a 2. My y, which is negative 2t. Last time it was a 3, now it's a 4. Remember, the x goes down by 1 each time, the y goes up by 1 each time. We're almost there. 6, then 3r to the 1, and negative 2t to the 5. My final term is plus the 1. Now I'm going to have 3r raised to the 0. I could write in 3r to the 0, but I don't want to. I typically don't. Then I'm going to have my y, which is negative 2t, raised to the 6. It's at this point in time, everybody, that I would check a few things. One of the things I would check is, do the numbers in the 7th row of Pascal's triangle match the numbers that I put at the beginning of each of these terms? So there are 7 different numbers in the 7th row. There are 7 terms that I have. The numbers are 1, 6, 15, 20, 15, 6, 1. When I look at Pascal's triangle, the numbers match the numbers that I have in my expansion. The next thing I want to do is check my exponents on my x, which is actually 3r. It starts off at 6, which matches n, and then it goes down by 1, down by 1, down by 1, down by 1, down by 1 until there's nothing left in the last term. Do my exponents on y start off at 0 and go up by 1? Well, there's no y's, which is negative 2t, in the first term. Then it's 1, then it's 2, then it's 3, then it's 4, then it's 5, then it's 6. I'll tell you what, everybody, the mathematics here so far is not difficult. You just need to be organized and clear in your process. There's a lot going on. Now we have some work to do to simplify this. When we take a look at the first term, I have 3r to the 6. Now I'm not going to write down this idea for every term, but 3r to the 6 means 3 to the 6 times r to the 6. So we have to figure out what 3 to the 6 is. 3 raised to the 6 is 729. So we get 729 r to the 6. Now in our next term, I guess I'm going to treat this side of my screen as scrap paper. In my next term, what I have is 6, and then I have times 3 to the 5, and then I have times r to the 5, and then I have negative 2 to the 1, and I have t to the 1. And this is again just scrap paper here. You certainly don't need to write anything down if you were doing this on paper. The bottom line is we have a number of things that are contributing to our coefficient. We have the number 6. We also have 3 to the 5. And then we also have negative 2 to the 1. So we need to figure out what those things multiply to give. 6 multiplied by 3 raised to the 5 multiplied by, in brackets, negative 2 raised to the 1. Whenever you have a negative number raised to an exponent, always put it in brackets. What we end up with is negative 2916, which means our second term is negative 2916, and it will contain r to the 5 and a t to the 1. What about our third term? Our third term is 15, and then we have 3 to the 4, and we have r to the 4, and we have negative 2 squared, and we have t squared. So again, we can calculate the coefficient by looking at all of the numbers. All right, so if I take 15 multiplied by 3 raised to the 4 multiplied by, in brackets, negative 2 raised to the 2, that gives me 4860. Which means that my next term is plus 4860. And when I look at my variables, I have an r to the 4 and I have a t squared. I've kind of run out of room for scrap work here, so I'm not going to be showing this anymore. I'm just going to be referring to it verbally. The next term that I'm going to be working on is this one, underlined in pink. When I find the coefficient of that term, I am going to need to multiply 20 by 3 raised to the 3, and also by, in brackets, negative 2 raised to the 3. This gives me negative 4320. So we have minus 4320. And when I look at the variables, I will have r cubed, and I will also have t cubed. We have 3 more terms to go. Let's take a look at this one. To find the coefficient for this term, I'm going to multiply 15 by 3 squared and by negative 2 to the 4. This gives me 2160. So we have plus 2160, and looking at the variables, I will only have r squared, but I will have t to the 4. Now I'm going to look at this term, and to determine the coefficient there, I'm going to take 6 multiplied by 3 to the 1. Well, 3 to the 1 is 3. If you want to enter raised to the 1, feel free. Multiplied by, in brackets, negative 2 raised to the 5 gives you negative 576. So my second to last term is negative 576. I will only have one r this time, and I will have t raised to the 5. My last term is going to be 1 multiplied by negative 2 to the 6. Negative 2 to the 6 is 64, but we can certainly confirm it on the calculator. So we end up with plus 64t raised to the 6. Which means that 3r minus 2t raised to the 6 is equal to that thing that we just wrote down. So 3r minus 2t all raised to the 6 is equal to this whole thing. We can certainly go to Wolfram alpha to confirm that that strategy works. So I've entered in 3r minus 2t raised to the 6 in Wolfram alpha. Under alternate forms, it gives us the expanded binomial. If I take a look at what they got and what we got, term by term, all of the coefficients match, all of the variables match, so we've got the correct answer. Now this is a very, very tedious process. So rather than working with Pascal's triangle, I'm going to show you a shortcut here. Now the thing that slows us down here is having to write out Pascal's triangle. There's some other things that slow us down, but Pascal's triangle is the really difficult part here. Because if I said to you expand x plus y raised to the 12, you're going to have to do 13 rows of Pascal's triangle. Well, let me write out the numbers for Pascal's triangle. It's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. It turns out, and this is really pretty interesting, that the numbers in Pascal's triangle are the result of using combinations. And I'm not even going to refer to row numbers anymore. I'm going to say to myself from now on, if I want to expand x plus y to the 5, rather than saying, oh, I need to find the 6th row, I'm simply going to use for the coefficients 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. So I'm always going to be choosing a number out of n. All right, example 2. we're going to use this idea of combinations to avoid Pascal's triangle. We want to write out the expansion of 2x minus 3y all raised to the 9. Specifically, we want to know the fifth term. And what I hope to accomplish by the end of this example is for you to learn how to find a specific term without having to write all of the terms. But let's start off by summarizing what we know. We know that x is actually 2x, and our y is actually negative 3y. Remember, we are always comparing what we are asked to work with to x plus y raised to the n. That means that n, of course, is 9. Now, if you wanted to work only with Pascal's triangle, which is a lot of work, then you have to determine the 10th row of Pascal's triangle. I'm not going to do that. What I'm going to say is that the coefficients of these terms are going to start at n choose 0 and go up to n choose n. Again, going back to this idea here, if n was 5, the coefficients were 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. So if n is 9, the coefficients will be 9 choose 0, 9 choose 1, 9 choose 2, all the way up to 9 choose 9. Now, we're not going to write all of those down because I want to give you a simpler approach here. The first coefficient will be 9 choose 0, and it will contain our x, which is 2x raised to the 9, and our y, which is negative 3y raised to the 0. All right, that's the first term. Our second term is going to contain a 9 choose 1, a 2x raised to the 8, and a negative 3y raised to the 1. This is our second term. Now we're after the fifth term. I'm not going to do this all the way to the fifth term. I'm going to do just one more. The next one would be 9 choose 2, 2x to the 7, negative 3y to the 2. And this would be our third term. And I want to point something out to you. And it's the key to working with the binomial theorem. This number that you're choosing out of n always matches the number that's on y. So when we're choosing 1 out of 9, the y, which is actually negative 3y, is raised to the 1. When we're choosing 2 out of 9, the number that y is raised to is 2. The other thing I want you to notice is that the two exponents always add up to give 9. This plus this give you 9. This plus this give you 9. This plus this gives you 9. And the last thing I want you to notice is that the number that you're choosing out of 9, which is highlighted in blue and which I like to call the key number, that key number is 1 less than the term number. So for the first term, that key number, which I call k, is 0. For the second term, that key number, the number in blue, is 1. For the third term, that key number is 2. So if we put this all together, if I ask you to find the fifth term, this is a way to write the fifth term, we need to say to ourselves, oh, the key number is 4. And if you can identify that the key number is 4, you can figure out the fifth term right out of the gate. Because it's going to be 9, choose the key number. It's going to contain your x, which is 2x, and your y, which is negative 3y, and the key number will match the exponent on y, and the exponent on x has to add to the key number to get 9. The top two exponents have to add to give 9. So this is the fifth term. And we can figure out what that is. I'm going to have to figure out what 9 choose 4 is. By the way, if you were to write out Pascal's triangle, you would discover that the 10th row, which is what you would need to look at to solve this problem, would have a fifth entry of 126. So you can come up with that number without using Pascal's triangle. We get 126. We have other stuff to work with, but I'm going to do this in stages. 126, then we have 2 to the 5, we have negative 3 to the 4, and we will contain as well in this x to the 5, y to the 4. So we just have to pull all of those constants together and calculate what the coefficient is going to be. It's 126 times 2 raised to the 5 times, in brackets, negative 3 n bracket raised to the 4, which gives us 326,592. So the fifth term is equal to 326,592 x to the 5, y to the 4. And we were able to find that without having to write out Pascal's triangle. We were also able to find that without having to worry about what the first and the second and the third and the fourth terms were. All of this stuff that I have written below, all of this is just so I could explain about the key number. You wouldn't do this every time. By the way, I'm just going to quickly go into Wolfram Alpha and enter 2x minus 3y raised to the 9. You'll have to trust me that I did enter 2x minus 3y raised to the 9, but you can see in the section that says expanded form, the fifth term is 326,592 x to the 5, y to the 4, which is what we had. So very briefly here, I know that we're done, but some of you are going to be moving on to calculus next year. I think this is a really important idea. If I gave you 4p minus 3q raised to the 11, and I said, what is the seventh term equal to? The key number for the seventh term is 6. So that means you start building this. You're going to have some number choose a key number. You're going to have your x, which is 4p, raised to some number. You're going to have your y, which is negative 3q, raised to the key number. And you can start building it. It's 11. Choose the key number is 6. My x is 4p. My y is negative 3q. This number is also the key number, and the exponent on the 4p must be 5 because those two exponents have to add together to give 11. I'm not going to actually calculate this because I think the numbers will get too big, but if you calculate 11 choose 6 and multiply that by 4 raised to the 5 and multiply that by negative 3 raised to the 6, then we'll have p to the 5, q to the 6. You would get the seventh term. This would be T7. So you don't need to expand it all out to find any term from now on. In your textbook, dealing with the binomial theorem are a number of questions I would recommend. Again, the lesson today, as well as the material covered in Monday's lesson, are not part of the final assessment. So I guess you could go so far as to say they're not part of what you're expected to know, and I'm fine with that. However, these are things that we've been covering over the past couple of days that will be helpful for those of you moving on to Math 31 next year or moving on to post-secondary mathematics. Anyway, I want to take this opportunity to thank everybody for their patience when I first got this going. I was running through some bumpy roads trying to get things organized, and it didn't always work out perfectly, but again, thank you for your patience. Thanks as well for your hard work. I hope that we run into each other somewhere down the road. This is certainly not the way I wanted to end the school year. I really enjoy that last day of classes with students where I get to talk to them about things that are going on in their lives and what they're planning on doing next year. But we can't do that, so all I'll say is that I wish you the best, and I hope that we run into each other from time to time. Good luck next year in whatever it is you're doing, and take care of yourselves.